All right, so let's say you're given this integral here, and the question asks you to compute the integral. To start, we should know what we're doing physically. When we take an integral in 3D, we're finding a volume. So when we take the integral in 3D, for example, in this picture here, we have to take the integral in one direction while keeping the other two directions constant. If the integral is dx, dy, dz, we have to convert it into this form here where we first take the integral with respect to dx. What does this mean physically? If we look at our graph, when we keep dy and dz constant, we just end up getting the x side length. And if we do the same for y, we get the y side length. Same thing for z, we get the z side length. We multiply all these together and we end up getting a total volume. So that's essentially what we're doing. So we can start off by computing the dz integral. If you remember, the integral of a constant is just going to be equal to the variable. So it's going to be z between the two bounds. Plug in our bounds, get this expression here, so we can plug this back in. But now we should analyze the bounds and determine the surface we're solving for, since this will simplify our question. So for our dy, we have these two bounds here. This is the same as a triangle of radius 1, because if we look at a triangle and use the Pythagorean theorem, if we plug in a value 1 and isolate for y, we get what our bounds are. So what is this y bound saying? Essentially what we're doing is when we're taking the integral, we're finding this distance here between the two bounds. And notice that our bounds depend on our x value here. So that x value is going to determine what our radius of the triangle is. By analyzing the x bound, you can see that it goes from -1 to 1. So what does the total picture mean? It means when we're doing the dx and dy, we're actually finding the area of a circle, radius going from 0 to 1. This means we can replace the integral with polar coordinates to simplify it. These are polar coordinates here, where x and y are written in terms of r and theta. And so how do we convert it? dy and dx is going to convert into r dr d theta. So instead of our integral bounds being a change in x and a change in y, it's going to be a change in r and a change in theta. There's an extra r here because of the Jacobian. So what are the new bounds? For r, if we look at our circle here, r is going from 0 to 1. This will ensure that we cover the full distance of the circle radius 1. And then if we analyze theta, to cover the full area of the circle in the integral, theta has to go from 0 to 2 pi to ensure that we cover the full area of the circle of radius 1. So we also have to convert our function. We have to replace the x squared plus y squared with r squared because that's our new variable. And if we put this all back together, we get this integral here. Don't forget to add this r here. That's easy to forget. So from here, we can start computing the integral by first multiplying the r into the bracket. We take 2 out, taking the integral with respect to dr, which if we use the power rule, we get this expression, plug in our top and bottom limits, and we get this value here for that integral. Bring the 1/4 out, and then take the integral with respect to theta. Do that, we get this value here, and then we can plug that back in, and we get this for the final answer. This is the final answer of the integral and represents the volume of the surface described by the integral given.